Okay, so we've talked about how to compute matrix inverses. So let's consider some properties. First of all, we'll go back to something I mentioned in an earlier video, that so far we haven't shown that the inverse of a matrix is unique. A matrix might have several inverses, but in fact, the matrix inverse is unique. Just like in ordinary algebra, the multiplicative inverse of the number 5 is unique. It's 1 over 5. Okay, so the way to prove that the matrix inverse is unique is basically you take A and you multiply on the left by B and on the right by A, and you interpret this two different ways. By associativity, that's the same thing as BA times C. But BA is the identity, so that's equal to C. But I could interpret this as B times AC. But AC is the identity, so that would give me B. Okay, and that's basically what he's doing here. B is B times the identity. The identity is AC. I can reassociate. BA is the identity, so that gets me C. Okay. Now this one is interesting. It's finding the inverse of a product of two matrices. Okay, so suppose A and B are both invertible matrices. Then AB is invertible, and AB inverse is B inverse A inverse. So just follow along this multiplication. If that's true, then I can multiply AB by B inverse A inverse on the left and get the identity. See how this works. If I take B inverse A inverse on the left, multiply by AB, then I can reassociate so that I do the A inverse A multiplication first. But that collapses into an identity. The identity times B is B matrix. And this product collapses into the identity. So the final result is that this product is equal to the identity. On the other hand, if I multiply on the right-hand side, I get the same result. I can collapse the B multiplication into the identity. A times the identity is A. I collapse, and then I have the identity. Okay? Right now, here's another property that follows fairly rapidly, that the inverse of an inverse is the matrix itself. All right. If A is invertible, then its inverse is invertible, and A inverse inverse is A. That's the same thing as saying 1 over 7 is equal to 7. Okay. Now this just follows from the definition. We know that if A inverse is the inverse of A, then A inverse is IN, and A inverse A is IN. But that means that A satisfies the same definition as the inverse of A inverse. Okay. It turns out that the inverse of the transpose is the transpose of the inverse. Okay. And you can follow along that proof. You use some algebraic properties of the transpose, that if I take A inverse transpose times A transpose, well, the product of transposes is the transpose of the products in reverse order. But that's okay because A inverse is still the identity. So I still get that A inverse transpose times A transpose is the identity. And I can do the same thing the other way around. A transpose times A inverse transpose is the identity. All right, these are things that falling past very quickly, but these are properties that you'll become familiar with as you use them. All right, the inverse of a scalar multiple, if I take the inverse of a multiple times a matrix, that's 1 over A times the inverse. Or I should say, if I take the inverse of alpha times inverse matrix, that's the same as 1 over alpha times the inverse matrix. And you prove this just by verifying that it works in the formula. Okay? Turns out that some formulas like this are not true. Now, in fact, this isn't true for fractions either. You can this is a common elementary mistake. If you take 1 over 5 plus 3, now that's certainly not equal to 1 over 5 plus 1 over 3. So if you think about fractions, a lot of the things that are true for fractions are also true for matrices. The only exception is that you don't have commutativity. All right, well, that's it for this section.